Can you guys hear me?
Yes.
Okay. Okay, let's start. Yeah, so today the presentation is about symmetry-based representations for artificial and biological general intelligence. So I think it's more of like a kind of like a theoretical paper. I would have liked if there was a little bit more like a kind of like a how we're going to achieve this, but I think it's a good compilation of kind of work that they summarized into essentially one main principle, which is like symmetry. And I thought it was interesting. So they start off by saying that biological intelligence skill acquisition is kind of unique compared to deep learning currently, still, because it's data efficient, it's generalizable, and it's transferable, which are currently not things that we can do with deep learning yet. And what they are saying is that neuroscience and machine learning are both kind of searching for what are good representations, right, that underlie these kind of like currently unique skill acquisitions skills. So like I said, like the bottom says, like these good representations are likely to be fundamental to achieve data efficient, generalizable, and transferable skills, essentially, skill acquisition. So I'll start off by explaining why we're interested in symmetry and these good representations, and then I'll talk about symmetry and equivariance, and I'll then discuss symmetry in machine learning and symmetry in neuroscience, which is also the kind of the way they go through the paper. Okay, so why are we thinking about symmetry, and why do we even want to get good representations? So our intelligence obviously was evolved in the physical world, and what they argue is that the tasks we find interesting are also similarly constrained. So most of the tasks that we find interesting, so like object recognition and things like that, are things that are similarly constrained to the physical world. I mean, there are, you can argue there's obviously more things that we're interested in now with the internet and stuff like that, but that's still kind of constrained to the physical world. I think what they're trying to argue is mostly that the main things that we're interested in machine learning currently are still very much like physical things. So then why symmetry transformation? So by saying we're kind of like evolved in the physical world and we're interested in tasks in the physical world, they take symmetry transformations as a fundamental idea in physics, which was they talk about, which I thought was a funny fact, or like a cool fact, is that Noether's theorem has proved that every conservation law in physics is grounded in a symmetry transformation. So, for example, conservation of energy arises from time translation symmetry. Conservation of momentum arises from the space translation symmetry, and you can keep going. He's proved that for every single conservation law. So that's interesting. And what they say is that physics, like modern physics, has used this idea of symmetry transformations to find new ideas, essentially, because it's such a fundamental property.
Hey,
What? Did someone say anything?
I just was curious when you said modern physics. I was expecting the quantum physics, but like all those laws seem to be valid in classical physics or classical mechanics.
Right. I mean, but modern physics is not just quantum. I think like just modern physics is just like the
the easiest example to give in a paper that we could understand. But I've heard PhD physicists talk about how their interest in symmetry it's fundamental to a lot of physics stuff.
Right, exactly. Yeah, it's probably also using quantum physics, but also to discover new properties of the world. Essentially, like it's just more of I mean, quantum physics is one of the modern physics field, but there's obviously more, like, it's not the
Yeah.
only. But yeah, I'd probably also use, I mean, they don't really go into depth about how physics are currently using it, because they're gonna use it to argue for their own thing, but I mean, I think they mentioned some papers. I mean, I could send them, I think, so they talk about the insight that transformations and conserved properties, the invariant cores of the world that words often tend to refer to, are tightly related has led to a paradigm shift in the field as the emphasis in theoretical physics changed from studying objects directly to studying transformations in order to discover and understand objects. So I think that's what they mean, and that's now modern physics doesn't study objects, but rather transformations. So at least, yeah, that's what I'm getting away with it.
Okay, that makes sense.
So it's like a modern way of looking at physics. Okay, so I'll just start by, I think most people know what invariance is, but I'll explain it anyways. So let's say we have a number of objects on the table and we want a neural network, for example, to count the number of objects. We want it to not care about the color of the objects, right? Which is also something that we wouldn't care about. Like if I were to count, 5 like cylinders on a table with different colors, I wouldn't care what the color is. I would just care about the number of them. And so that's what invariance is. You don't care about the color, and machine learning has historically emphasized this. There's multiple different ways. I'll give an example in a second, but it essentially, at least by definition, invariance kind of discards information, and they argue that this likely leads to worse generalization. I mean, not just them, but like a bunch of people argue that. And one of the reasons that people started doing that is also because the visual stream progressively discards information. So for example, in machine learning, this would be an example of invariance. So you transform the same teapot, the features within the neural network do not change, and the final prediction that it is a teapot does not change. So it's completely independent of symmetry. But what they argue is that now you lose the information of this, and maybe on new tasks that could lead to worse performance. So this is what an example is in neuroscience. So what they used to think is that when you have the V1, which is the first visual region, V1 entangled representations, which kind of have this activation that isn't clearly aligned with any specific attribute. For example, these robot figures, goes to, at the end of the visual stream, towards exemplar/invariant representations that are that, for example, completely code for blue and do not care about anything else. That's one of the examples they give. But there's also an alternative, which is equivariance. And so the difference here is that in this case, the information about factors are preserved, but they're reformatted such that they align with the transformation of the real world. So for example, if we take the coffee pot or the teapot, what would happen is that you would still see a difference in the representations, but you would still lead to the same prediction, essentially. And I'll give you an example in a second. So both in neuroscience and machine learning, they think that equivariance is likely important to support this like general intelligence idea. And they call this finding these like sort of equivariant representations, they call that disentangling. So this is the example. It's not very obvious, but you can see that this teapot is now transformed, and instead of these features all being exactly the same, you can now see that the features at the end here and at each layer are also transformed with a 90-degree transformation. But the final representation, the final prediction is still teapot. So instead of losing the information of the symmetry, it occurs in the features of the neural network. It's just that it doesn't care about it to predict the final thing. So that's an example of a very simple example of equivariance in machine learning. And this is what equivariance machine learning would look like. This is what equivariance would look like in the final streams of the visual cortex. So for example, now the information is still there. For example, you have this axis of like different types of ways of robot, and then a separate axis of I guess the head of the robot. It's a little bit, I'm sure you guys understand, even if I did, like, this is just, I find the figure not to be super informative, but it's just that you still have the other dimension now. It still occurs, but it's completely axis aligned, if that makes sense. So you don't throw anything away. That's the idea. Okay, so what are symmetries? So I'll just follow them in terms of their mathematical definition. It's not very complex math. But for example, a group in group theory in mathematics, one of an example of a group is the dihedral group, which is all the rotations by multiples of 90 degrees. So that's shown on the left. And then what they mean is that, for example, here, like if I have this as an object in the set, this teapot, then each of these are different in the set. But if my object is this what's it called again?
Teapot.
Yeah, but like it's flipped. Like, what's it called? Mirrored. This mirror teapot, then these two are invariant. These two objects of the set, and these two as well, the bottom and the top.
Mm-hmm.
So you can still have invariance within equivariance, but equivariance is just a more general property. So that groups, I mean, it's not a super complex definition, but a group times a group remains in that group. And two members within the group. This is how you define composition and multiplication of the group. And these are the three fundamental aspects of the group, is that every operation is associative of elements of the group. So G1, G2 are elements of the group, and you can, they're associative. There's an identity element, and they're inverted. So those are the main definitions of the group. And then you can also talk about a set and actions, where you would say that if you have a group G and a set X, multiplying the group and the set results in the same set. And this is how you would define multiplication between them. And these are the properties you have. So the multiplication of the group and the action are compatible. So again, they're like commutative in a way, like G1 times G2 times X is the same as G1 times G2 and then times X. And the identity of the group leaves elements of X invariant. So these are just some mathematical definitions. I mean, yeah, I don't really think they matter that much. But so this is the main important part that they talk about in terms of mathematics, which is that if you with invariance, when you're talking about this this transformation F, we can, if we have this transformation F of X equals Y, we can now not distinguish between X and G times X, where G is an action that F is invariant to. So let's say we're talking about the teapot and the 90 degrees angle. G would be the act of turning the teapot 90 degrees, but we wouldn't know if we had Y whether X was straight or a 90 degree, under a 90 degree angle. So that is what they're saying here. Now, if H is any map, then it is not generally true that F of H of X is invariant. So if we first do H, if we first perform H on X, if we first transform X using H and then using F, doesn't mean that F is now still invariant. In fact, it's only invariant when H is an equivariant transformation. So, and they prove that, but the main point to remember is that this is how you define equivariance essentially, is that you have this map H, and then you can take the G, this action outside, because it doesn't matter if you do before or after. And that here you can see that, let's say we do G on X, and we can take it outside because of the equivariance, and then we can see that that is still the same as H of X, F of H of X. And what they're just trying to say here is just a mathematical way of saying that with F of X, you remove a lot of information from that you may need later on in, for example, transfer learning or generalizability or something. So it's a little bit of a side road, but I think it is still good to define these things mathematically because it's not very complex. Like it's not, I don't feel like it's too mathematical or too mathy. They're not trying to make it seem more interesting than it is. It's very kind of like straightforward. So what are some examples of equivariance in machine learning? So convolutional neural networks are a great example because they're equivariant to translation symmetry. And then we have graph neural networks and attention, which are equivariant to full group of permutations. However, linear layers are not compatible with any particular symmetry, so they're not equivariant to any of them. Although MLPs have obviously been shown to be universal function approximators. So it's interesting that it's still a universal function approximator, but they're not equivariant. And one of the main ideas here is that you can reduce essentially this volume of the input space using symmetry. So if you look at this cube, you know, we can learn the whole cube, but if we know there's symmetries that occur, for example, left and right side are symmetric, or there's symmetry across these four parts of the volume, we not only have to learn this part if we know that the rest is equivariant to the rest. It's equivariant. Yeah.
I kind of want to hold my questions to the end, but I just want to ask this in case you're not going to mention it. All right, like, are you going to mention how this impacts data augmentation and stuff like this? Because
well, yeah, but data augmentation, they say often is invariance. Is invariance. So I won't get to it, but they actually say that data augmentation is not a good idea.
Yeah, I mean, that's the kind of like what I was like hoping you point out. I was like, seems like the more symmetry is able to handle by the network, the less data augmentation you need.
Yeah, that's a good point. Yeah, so that is if you build, so essentially to rephrase, if you build symmetry into the model, you don't have to do data augmentation to have it learn it. Yeah. But they also say that data augmentation is a little bit, you know, practically works, but it's not like the best way of doing it. There's like a lot of issues with data augmentation because obviously at some point you have to do data augmentation for everything. Like it's like this, it blows up in your face because you have to do so much data augmentation. Instead, if you would make your network kind of like architecture equivariant to the thing in the first place, you don't have to do these data augmentations to have it learn different things.
Yeah. That seems to, I mean, and that was, I asked like Alex the other day if there was any networks that were known to be robust for this with MRI, because like the thing I don't want to do is have to like have a bunch of data augmentation of MRI, which is really computationally expensive already. Right.
So what they say, for example, is this principle of like building it into the architecture. First of all, it is hard, right? It's not like simple or something, but it has been used before, and especially in scientific applications of machine learning. They mentioned like protein folding. There are specific neural networks that are equivariant. In fact, Max Welling does a lot of research in equivariant neural networks, but also quantum chemistry. You know, you want to have certain equivariant like properties of your models to make sure that you don't have to train on every single like protein, for example, or every certain like different rotation of a protein. So that's what they mentioned. Let me see. So what you can imagine to like put your question into context of the image. Let's say if we make an equivariant network, we only have to train this part, this like square, this blue shaded part. But if we were to use data augmentation, we would essentially have to do data augmentation of this whole cube, right? We'd have to make sure that we cover this whole cube of like space of transformations.
Yeah, it seems like there's like two options. You can either make an equivariant network, or you can make sure the input is like always like normal, like canonical, like always coming in like centered and
Right,
mapped.
but that would actually mean that you probably have some sort of like inverse equivariant network before it to make sure that you make it
Right.
exactly the same. So yeah, this is actually a good. They're gonna talk about it now. So they don't talk about it in a very like direct way, like, oh, you should do this. But they just mention like a couple of high level ideas. I mean, they cite a lot of papers. So if you want to look into any of these, I can point you to the section of the paper that they talk about them and see what papers they cite. But so what I mentioned just now is like literally building them in. That is like making equivariant networks. So this is often done in scientific applications because it's computationally expensive, right? So it's like easier at some point to just make them equivariant. Also because you have a lower chance of it failing, right? Like data augmentation works practically pretty well, but you still have no like guarantee that it won't be that it will be invariant to these things. And oftentimes it also means invariance, which maybe is not a good thing. You know, like for example, if the brain, I mean, in the neuroscience space, like maybe later on, if you want to use it to generalize these tasks, maybe it is good to know whether the brain was rotated or not, for example. Like, you know, you shouldn't maybe use it for classification, that feature of like whether it's rotated, but to have it as a feature in your lower level representation may be a good idea for like generalizability. So that's what they kind of argue is like you're throwing away information that you don't know if you're going to need later if you're making it invariant to something, because that's the point of invariance, that you throw away information. So that's the first one, literally building them into the architecture. That's one. There's like a lot of papers on equivariant neural networks and stuff like that to specific symmetry groups. So for example, like translation and CNNs, you could argue, I mean, literally translation is a transformation, and you can be equivariant to the transformation. Then there's data augmentation. And they specifically mentioned that recent works have shown that it's especially like less effective than building them in. Doesn't mean that there isn't a place for data augmentation, you know, but like it just if you're talking about the theoretical idea of like building in these symmetries, it is less effective than the other ones. And then the third is to adjust the model's learning objective to make sure equivariance is added by using regularizers or by explicitly deciding what good representations are. So you could, for example, say, okay, I'm going to make this network learn as a first feature color, as a second feature orientation, as a third feature rotation, et cetera, et cetera. So either regularizers, which are unsupervised, or by explicitly deciding what is good. So now they mostly talk about this in this paper about the third one, because they think it is more related to the brain. I think that's a fair argument. I mean, there's probably also equivariance in the brain, but equivariance transformation specifically. But it makes sense that the brain mostly uses a learning objective to achieve these kind of like disentangled representations, is what they call them. And in this case, disentangling, you could just think about like, if you have 4 dimensions, then the axis of those dimensions are aligned with a certain attribute. So let's say color, like I mentioned before, orientation, or rotation. That's what they call disentangled representations, is that it's axis aligned. If you go back here, you can see here that it's not like axis aligned, it's what they call entangled. And then this would be disentangled, where you have an axis codes for a specific type of attribute of the robot. Let's go back.
There's also limitations to our ability to handle equivariance, I guess, because like there's been like psychology studies that show like if you recognize people face on and then you see them in public like sideways, your ability to kind of handle that is reduced. And
yeah,
recognizing a picture upside down is a little bit harder.
Yeah, for sure. So what they're essentially also saying is like, if you're building in equivariance, you have to decide what the equivariance is. Whereas if you're doing this like idea of like disentanglement with like unsupervised, they don't explicitly say this, but I think that's kind of their point, is like, then you find the things you want to be equivariant to, like from the data automatically. That's kind of their, right? It's like a much cheaper way, because you can imagine that building in all the equivariance in your system is like pretty tedious and hard, because you need to think about what do we want to be equivariant to, and you can make mistakes if you do something like that.
Yeah, I think like almost all of the neuroimaging processing we do is this, what you're talking about. It's like getting to the point where it's like, don't need it anymore.
Right. So Alex adds, yeah. So this is I was kind of trying to make this point too, but I think this is a good way of putting it. So Alex said this: the number of configurations that you have to cover grows exponentially with the dimension of the input space. Yeah, exactly. So if you can, for example, if you can make it equivariant to rotations, you already don't have to do any data augmentations for rotations, which means that helps so much with like how computationally expensive it is to train models, or how long it takes to train a model. Because if you want to do data augmentation well for like rotations, you have to have a lot of rotations in the data set. So let's say you take 1 degree, you have 360 types of rotation. That's just the rotation, right? So it's like you can really make it much more efficient if you are able to build in these equivariants. But they're mostly targeting like this learning objective idea, like disentanglement using unsupervised regularizers. So
I bet you this would have like high transfer learning value too, like if you could like separate the network into like the part that's like covariant. I mean, in theory, even the feature extractors have a high transfer learning value that we probably don't take advantage of now.
right, that's what they're kind of saying, is like this is fundamental to like general intelligence, and thus also transfer learning and stuff like that. So disentangling generally is a framework where you can think of it as like, you can describe the world as a small number of independent generative factors. That's essentially the whole point of disentanglement. And finding these independent generative factors, that's kind of the process of disentanglement, where you have an entangled input signal, let's say our vision, and then we disentangle it into things like color and like pose and like stuff like that. So the goal is to infer a representation that is decomposed into independent subspaces, and these independent subspaces can be attributes like color, where each subspace is affected only by a single subgroup of our original group of symmetry transformations. So if we go back to rotations again, that would be a subgroup of our original group of symmetry transformations, and the idea is that this subspace, one of the subspace that you learn, is affected by the rotations, but all other subspaces are not. It's a technical way of saying the same thing that we were kind of talking about before already. So this is an example. Again, they have a lot of these similar types of examples, but this is an example of like a group of symmetry transformations. I'm not going to go too deep into these, but like what they say, for example, is that scaling, translating is commutative, because if you take this image and then you translate it and then you scale it, that's the same as scaling it and then translating it. That's their point. I think that's kind of obvious. But so their point is this: like if you're doing this in neural networks, this is the thing that you have to look at. There's like, you have this input, then you do inference, and then you have a representation with, in this case, 4 dimensions. I'll read them to you because I think it's hard to read: shape, size, color, and position. And what they're saying essentially is like, is that, let's say we traverse these dimensions. So let's say Z1 position. This is after you train the network, by the way. That's why it's called inference. You can traverse this dimension, and then you can see like the red cylinder move as well. And then you also have a dimension that's scale, and you can see that the red cylinder increases in scale. I think they do this based on an actual neural network they trained. So, but you can also imagine color and shape, that they are different disentangled dimensions that they find. So, I mean, they say that disentanglement in ML currently is often done using variation autoencoders. I think my personal opinion is that they shouldn't. I understand. I mean, this specific author works a lot with BAEs, and although I followed them a lot through like their research, I understand that they say this, but I think they shouldn't make a claim that, it almost sounds like you can only do it with BAs, but that's not true, I think. And in fact, they say that BAs have been proven to be theoretically impossible to do this. But the same paper that says that it's theoretically impossible also says that actually practically they do it very well. So it's this weird dichotomy, which is, I think, often the case in neural networks.
Question.
Yeah.
Do you mind sending a link to that paper in particular?
Yeah.
To a Slack channel?
Yeah, sure.
Because that'd be interesting to see how they prove that.
Yeah.
It's possible.
No, I will. I think it's interesting because, I mean, this is just the common dichotomy of deep learning. I mean, we also have too many parameters to actually do anything meaningful, but somehow we still do. And then the second thing is that for reinforcement learning, they find that agents with disentangled representations could discover generally useful skills that could be readily used for solving new tasks. So that it's like they don't mention reinforcement learning too much, even though there's a lot of work in reinforcement learning in this specific field. They mention it a few times because it's so interesting, but this again speaks to like this idea that if you have disentangled representations, you can more easily like transfer and you're more generalizable and stuff like that. And because RL in some ways is closer to like what humans do than let's say supervised learning. So then the next part, symmetries and neuroscience. So as you can see, it's a pretty like open-ended idea paper, which I do like it, but I would have liked it to be a little bit more like down to earth, like, okay, this is how you can actually do it. But still, I can imagine, I mean, it's already hard to write all of this in one paper. So okay, so symmetries and neuroscience. Well, the same idea of this like disentanglement also has been, said many times in neuroscience and especially recently. And they'll give a few examples of it actually. So first of all, we know that there's factorized representations of independent attributes such as orientation and spatial frequency or motion and direction tuning in the start of the ventral visual stream in V1, which like that's more like these like filters essentially. But then there's also evidence that demonstrate that IT neurons, which are I think deeper, they have monotonic tuning to more generative dimensions of like toy visual stimuli. So this is another paper that they cite where they find that the neurons have, so they're kind of disentangled with respect to generative dimensions of toys like curvature, tapering, or aspect ratio. I think is pretty interesting, but yeah, so that's where they begin. And then they start talking about, so these are some of the examples from papers they take, is like neurons, like firing of certain neurons is modulated by attribute. And so again, this is disentangled because it only starts firing with one specific dimension of attribute and not with the others. So you can see that it doesn't fire with this attribute or this attribute. It only fires with kind of this attribute where it's the roundness of the shape. Seems like, and then these it also doesn't share, it also doesn't modulate with these. And then other neurons, you can see that here doesn't do anything and then only modulates with this attribute. So kind of this roundness. It's the same type of attribute, it's just a different shape that they make more round. Yeah, so that's their point, is like, hey, this also happens in the visual stream. This is one example, and then they go further, and then they say, well, look, neurons are also sensitive to the axis of faces, where STA means the spike triggered average. So what you can see is that this is the spike triggered average. This is the axis they find is the spike triggered average for the faces, and this is a principal orthogonal axis, so something that is completely orthogonal to this axis of variation. And what they show is that if you change these axes, they only modulate with this axis of variation of the people's faces. So that's something they find. So that's again, they say that points to disentanglement. This is kind of the same idea, but in different view essentially. which means that, see, like it only changes across, the color only changes across the x-axis and doesn't change across the y-axis, where the y-axis is orthogonal dimension. A variation of faces. So this is another paper they kind of show as like an example of disentangled representation of the brain. Then they actually do one where they compare a variational autoencoder latent dimensions to neurons in the brain. And I'll talk about this a little bit more because I'm very skeptic often of these kind of comparisons with like directly with neurons, with neural networks, but they actually have an explanation why they're doing it much better than other papers that have been disproven recently, especially in the past 2 years. But yeah, they show that like specific latent dimensions for your VAE can code to the same attributes as like neurons are coding for. So neuron 95 codes for hair length, and the variance explained of the VAE is like about 0.15 for this neuron. Then you have gender, which another latent dimension, namely 3 codes for, and neuron 117. You have face shape, which is neuron 140 and latent dimension 4. Then fringe, which is neuron 51 and latent dimension 5. You have smile, which is neuron 136 and latent dimension 6. And then age, which is neuron 68 and latent dimension 10. Yeah. Although I think this one is not as good because you can see that there's other neurons coding for the same. Anyways, so like I said, I'm a little bit critical of these types of things because there's been some questions about whether representational similarity is actually a good way to assess whether neural network code for the same thing as neurons in the brain, which is partly because variant explained and representational similarity analysis is invariant to linear transformation. So you're essentially throwing away linear transformations, which is a little bit simple. So the previous figure that I just showed means that there's a one-to-one alignment. So it is not invariant to linear transformations. It's literally a one-to-one alignment. So, and it's with a single person, by the way, because they also say that doing this on a group level is not a good idea because the same neurons in different people may not code for the same thing because, you know, because on a neuron level, makes sense. So this means that there's a one-to-one alignment. So that it's not invariant to linear transformation, it's one-to-one. So I think that makes the argument much stronger. And they also say that the alignment is significantly stronger than that with supervised classifier in other works. So I don't know if you've guys seen the works where they try to kind of see how similar supervised classifiers are, like layers in supervised classifiers are to the brain. Well, they say that's all cool and all, but this unsupervised network is much better in terms of the variance it explains of neurons in the brain than the supervised classifiers. Also because a lot of these supervised classifier papers use representational similarity, which again is invariant to linear transformations. So, and another thing they say is that they can actually visualize novel faces that the primates are viewing from the activity of the neurons, and then matching the 12 neurons to the best matched disentangled unit. So if we go back, you can see there's 10 dimensions they have, but they can do it with 12, and then they can reconstruct the face that the primate is viewing. So I've looked at this paper a little bit, but that does sound pretty cool. Okay, then there's a few other examples. Disentangled representations can predict fMRI activation of the visual stream, which that is cool. I think disentangled representations can arise from solving numerous diverse tasks in a supervised manner. So you don't have to train a unsupervised network per se, but you could also train a supervised network to do a lot of things at once, which also leads into disentangled representations. I think the reason they have, or they don't really give this reason, but I think the reason is because if you're trying to do a lot of things with a bottleneck representation, it needs to find very efficient dimensions of variability that it models. Otherwise, it can't fit all of the information necessary to do all the tasks at once. And then the last one is that the final layer of an MLP trained through reinforcement learning supervision to solve a number of tasks, as well as the dorsolateral prefrontal cortex, the anterior cingulate cortex, and the hippocampus of primates they all exhibit disentangled light qualities. So both the final layer of the MLP and those regions in the brain, and they show that in this following figure. So, where, by the way, the degree to which disentanglement was present is predictive of success on the tasks by the primates. So they're talking about not about the MLP final layer, but about these specific regions in the brain: dorsolateral prefrontal cortex, anterior cingulate cortex, and the hippocampus. The more disentangled those representations were, the better the success was of the primates. And they show this figure. This is related to that to what I was just saying, but I don't really like this figure that much. But they're essentially saying like this is disentangled, and it's doing all three well. Where the orange is the number of variables that can be decoded by a linear classifier. The kind of like blue-green is context. And value, and the green is value, which is the ability to generalize to novel situations.
I have a question.
Yeah.
Okay, so they're saying that the more disentangled the spaces are,
Yeah.
the better it performs. Have they shown the relationship, or did they even talk about the relationship between disentanglement and the training process? Like,
No, this is for the brain.
I thought,
No, this is on primates here, on task by primates.
oh, I thought they were comparing it.
No, that's what I specifically tried to say, is that they're not talking about this MLP, they're talking about the primates for this one.
Okay.
Yeah. No, otherwise it would also be a little bit, by the way.
So they don't talk about this as the relationship between this and.
Okay, so what they're trying to say here is that, first of all, okay, so let me rephrase a little bit. Reinforcement learning is often related to things in the brain, such as these regions, like dorsolateral prefrontal cortex, anterior cingulate cortex, and the hippocampus. They're often related to being similar, performing similar actions as reinforcement learning, which is a little bit of muddy water, but you know, that's what they often, but so what they did is they said, we're going to train an MLP through reinforcement learning supervision to solve a number of tasks. We're also going to have primates do the same number of tasks, right? And then we're going to look at whether how disentangled the final layer of this MLP is, and how disentangled these brain regions are, the activation of the brain regions. And they specifically say that the degree to which disentanglement is present in these brain regions in the primates is predictive of how successful they are on the tasks. These primates are successful on the task. That's what they're saying.
Okay.
Yeah, and then they say, so this is roughly the same for both. So here they're saying like these are the regions that they use, right? Prefrontal cortex and the hippocampus. They're saying that this is the sweet spot, which this is disentangled essentially. So they're saying here high dimensionality, multiple abstract variables, then you get more of the orange and less of the other two. If you have low dimensionality and multiple abstract variables, then you get kind of a best of all worlds. And then if you go to very low dimensionality and one abstract variable, you get a very high context, abstract context, and very low value and the orange. And the first one is high dimensionality and no abstraction, which then you're only good at the shattering dimensionality instead of good at value and context. I didn't like this one too much, but I think the other ones are more.
So did they control for any other confounds? So like if they just trained this MLP and said, oh, these primates are, their regions are more disentangled or whatever. If that's all they did, like, did they not control for any confounds? Did they not show that like, oh, it could be any number of other reasons?
What do you mean? I mean, predicting the success of the test.
Yeah.
I mean, this is a paper they signed, by the way. It's not in the, like, they don't do all this stuff in the paper. I mean, being disentangled, what would be the confounder of being disentangled?
I don't study primates.
Okay, but I mean, I was wondering when.
I mean, I'm assuming there's lots of confounds. Like, why is that specific primate more disentangled? Why is blah 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 blah? Is it size? Is it shape? Does it have other relationships?
No, sure, yeah.
Right.
I mean, I would have to look at the paper itself. I think it's an interesting comparison, but I don't really think that. Yeah, I mean, you would have to look at favor. They don't talk about it in this one specifically. I think, I mean, it's mostly just a combination of all the work that's been done in this area. So it's generally high level in all of the studies. I try to understand what the studies are doing specifically, but it's hard to understand all of them. Sure. Then the last argument they make is that there's a lot of similarities in the data distribution between what, for example, a toddler sees. This is from the IT Toddler Project. Did someone want to say something? I'll just continue. What toddlers see and kind of the distribution that we can learn on with our machine learning algorithms. That's the point of this, is that like the data distribution is very similar. There's similarities between the data distributions that we've worked on before as visual inputs and training sets that we have currently that we're using. And then this is the last one, where in this case, what they've done is like have people disentangle what they think are different like attributes that are important. So cupiness and color, for example, that's the left one, and then the type of cars. And they line up with what these neural networks are finding, essentially as like disentangled distributions. That's the thing. So yeah, the conclusion is let's disentangle. But my personal takeaway is also that we should just build in these literal Equivariant transformations into the inductive bias models. Because as much as I like the idea of finding all these things unsupervised, I've done a lot of research now with fMRI data and stuff. It's pretty hard on like more noisy data sets. And like, I like the idea, but I wonder how far you can push it, because these data sets that they have, like, for example, this is a data set, right, where they have like different circles in the image, a different location in the image with different sizes and stuff like that. And that's cool, but how, like, you know, we need to look at how applicable this is to the real world. Like, how far can you take this, right? The fact that you can disentangle this, I think it would be cool if you could disentangle more complex things, but the fact that we can disentangle this and, like, for example, chairs, I'm not sure if that automatically means that we can disentangle everything with these types of models, like if we need something stronger or not. But I do think the idea is cool, like also to think about the fact that we need things to be equivariant instead of invariant per se, and that we should do disentangle. But again, I think what's also very interesting here is to build in symmetries into the inductive bias, because they kind of gloss over it a little bit, but I mean, building them in is often done in scientific applications. And I mean, most people here are doing science. So, you know.
So they actually
some
don't talk about how they do it.
I mean, they just say like, oh, VAEs with like beta VAEs. Yeah, so it's more of like a theoretical idea. I mean, it's more about the idea, so you were here
That
before.
answers my question, actually, beta VAEs.
Yeah, but so Alex, I don't agree with that. I mean, at least the way they put it, is that you make it more discriminating. Because what they're saying essentially is like, but it's also a little bit of like I think currently there is still a trade-off. So I agree with you on that. But what they're saying is that if you find truly equivariant representations of things that you're interested in, then it's going to be even more discriminative. I don't know what you mean. Can you?
So they showed that the disentangled regions of the monkeys were more predicted, but they didn't show that was true for the models, right? So do they actually back up their
What do you mean?
do they actually back up the idea that models that disentangle more are more predictive, as opposed to just, oh, it happens in brains?
No. It's they have like a lot of papers they cite, especially for like transfer learning. I mean, the question is really like, what do you mean by discriminative? because just being good at discriminating different classes is also something that needs to be transferred.
So I
And if
mean,
you
I think
have,
this is all in the context of transfer.
right,
Or pre-training.
exactly,
whatever
yeah.
you wanna call it.
So what they're saying is, once you have equivariant representations, automatically that means it's more discriminative because it transfers much better. So you've really truly learned what the class is instead of just something else. Right. I'm reading your stuff out, yeah.
Alex. Alex, what are you saying about the information bottleneck?
Yeah, I also don't understand what you mean there.
So I just mean like, for example, you take regular CNN and do supervised learning, right?
Mhm.
And you don't have to kind of disentangle at all anything. Like example, like when you disentangle, you probably got something like orthogonal, I would say. Like you have like something that like you can control, move a bit, and like something will change, and it have to be mixed again to produce the result. So it's like you're trying to find like something you can control, and it's more like probably the question is like whether like we don't overfit this kind of disentanglement, because like when we run just like regular CNN, like with supervised learning, we get like higher performance usually.
Mhm.
But like when we run like VAE, we usually don't get like high performance, but we get like interpretable kind of representation.
So, but I think the different, yeah, but so that's why I think putting this V forward as the only way to disentangle is not, that's not their point. So that's also not why, I don't understand why they put it like as something, as their main thing that they compare it against. Their point is not, by the way, at all, that you should just be using VAEs to do discrimination of things.
Yeah, I just want like probably just to say that we should have like two kind of research. One is like focused on understanding of mechanism, like for analysis. It's more like scientific tool. And the second approach, it's like predictive, where it's like we're not like about understanding the mechanism. We want like to get the highest performance we can. And for example, as a application like for neuroimaging, in one case, our lab like using ICA to understand the brain, but like when you use like CNN for classification, you want to use like it for preventative measures like scanning people for cheap and faster and find the earliest time where like they have like first symptom of disease.
I understand, but by the way, I don't understand with the last part because I still think we need to understand why the neural network is predicting those things, but I do understand your general idea. Yeah, I think narrow AI is going to be better at certain tasks than general AI, but they're generally talking here about like trying to achieve general AI. So like, can you get so like humans are the best example of general AI that we have. That's their kind of their point.
Yeah, I probably want just to say like limitation of like disentanglement when you're trying to find like factors of variation, you're probably like dealing with noise. And it might be the case that you reduced like something which is important, and maybe like noise is important too, because like humans also like dealing like with a lot of noise, and maybe noise like helpful. And because like
But if it's
like
helpful,
recent
it's
work
automatically
is
not
like
noise.
diffusion models, like they creating something from the noise, right? So like there is probably like some importance in the noise, and we can't just like remove it like and like simplify it. So it's more like you have like simulator with idealistic like kind of variables that you can control, and like in real life we dealing like with a lot of kind of entropy and like noise, and to some degree like noise is important too. And
Alex, you're basically referring to spurious correlations, right?
yeah,
So any noise.
but like it's
Oh,
hard
yeah,
to
sure,
say.
right.
Like probably I will just stay in the point that like we just need to focus like on two different kind of applications for neuroscience, like in the sense that we want to predictive learning and we want to do something that can be used for analysis, and that's why like we can do, like, for example, my case, I have a model that kind of learns multimodal links between each other, but it's not like performing well for kind of discrimination. But if you kind of adapt the model, you kind of losing all the properties that you learned. So even like you use this entanglement model and then transform this model to like predictive task, you will lose all those kind of things that you learned. So
Well, I think their argument is that that's not true in terms of
yeah,
like,
it might be not true, but like maybe the reason is because like we get like spurious correlation, and the real performance we get only through VAEs or disentanglement. So
okay,
maybe
but I think the point of this paper is not to say that there's like currently a practical way of doing this. I think their point is that we should be searching for it, and that then it's better than a lot of the, like, you know what I'm saying?
yeah, like in the end, I still want to understand. Like I'm just saying that
Because I don't know if there's a trade-off between the two.
because like probably like the missing this like kind of limitation part, and kind of they want to like take this topic and talk about it more like with respect that other direction people can do it. Like I
Right.
think in this kind of questions we will learn more than like just exploring only one direction and saying this probably is the way. Like I just want to see maybe this comparison more, and I think we can't answer like this question right now, and I think it's the topic of research.
Yeah, because I do agree with you that yes, you know, like currently, I think there is definitely a trade-off in practice, right? If you want to do like a good discriminator versus something that disentangles well. Because, you know, VAs are, I think, not that good at discriminative tasks. But I think, I mean, their point is not really to say that VAs are like the holy grail or that it's already been done. Their point is more that we should be thinking of finding representations as finding representations that are equivariant specifically. And that if we find a way to gather these representations from data, or like, you know, exhibit them on data, that's going to lead towards good representations that are both biologically feasible and better for performance on a lot of things. Maybe not all tasks. There may probably be some narrow AI tasks that are that like, you know, are still better by just training a classifier on them. But I think their point is that, yeah, I think that's their point. And I think the reason they focus on VAEs is just because that's like been a big like research area for a lot of people that are doing disentanglement. But like I said, I don't think VAEs are per se like the architecture that is the best equipped to do any of this. Like it's just one way of looking at things. You know, like ICA is
ICA is also not always more discriminative.
no true, but like
That's,
but it's a way of doing disentanglement.
yeah, no, that's what I'm saying.
Right.
It, I would say in maybe many cases, it's less discriminative than
Right, but that's-
certain kinds of.
But so what they're talking about is a theoretical idea, not per se the practice currently, because yeah, that's true now, but if we can really find the actual generative factors for something, then that will be more discriminative than other.
So Alex brought up IB, and thinking about it, I think that's actually a really good point. So you have to ask yourself, are these, because as the model trains generally from what all the Andrew Sachs and the T-Schbees have found, is that as the model trains, the latent space, the distribution of it shifts from being close to the input to close to the output. And so, well, generally. So you have to ask yourself, like, are these disentangled states, are they going to have a distribution that is similar to the input or similar to the output? how is that distribution going to change from disentangled to entangled?
What do you mean? And how does the information bottleneck play into that?
IB shows the relationship between the distribution of the latent space and the output compared to the relationship between the latent space distribution and the input.
Right, but in this case, the output is the input.
We're talking about the discriminative case.
Well, they say actually that discrimination algorithms are probably not good at it,
Okay.
right? So,
But they had a whole section in which they're like, oh, monkey brains are more disentangled, and so when they're more disentangled, they're better in the discriminative case, and so.
no, it's not discriminate, it's not discriminative. They're better at the task, which is like, for example, they're faster at finding a face. That's different than discrimination.
That's not their whole point.
Reaction
That
time and stuff. I think that's how they do performance. Also, that's not at all their point. It's just a little thing that I added because they mentioned it in their paper, but it's not at all looking important. In fact, they argue against discriminative models. The only discriminative model that they say is a good idea is to have a discriminative model learn a lot of different diverse tasks. That's the only thing. And then you can argue with the same argument that you're saying, like the distribution will then reflect all of the
might be
tasks.
saying two different things. So they in nowhere say that once you have these latent spaces, once you've trained them,
Mhm.
you should never judge them based on a task, downstream task.
No,
A
but that's not what-
discriminative downstream task.
That's not at all what it's about. I don't, what do you mean? They don't talk about that at all.
I mean, the monkey brain thing. That was their whole, it seemed like that was the whole point behind their comparison. Why
No,
they brought
No,
it up.
their point is this. Literally just this, that the trade-off is better if you do have disentangled brain.
Yes.
Right.
Yes. They're saying that has nothing to do with the latent spaces of said model.
They're saying there's a correlation between how disentangled the brain is and how well they were performing on tasks.
Okay, so Alex's point was essentially, maybe these models can perform better on tasks, any task, doesn't matter what it is, than what the living brain can perform.
No, I agree. with that.
And so if that's the case, then this idea of like, well, we should find latent spaces that are both discriminative and disentangled. Well, you probably. from what I can
Maybe I'll try to explain like my point. For example, you find like idealistic, really like disentanglement representation, like latent representation.
Mhm.
But since we like working in the like noise environment, so the codes have to be robust. But how like you make like code robust, like you reducing your like coding efficiency, but like you doing like trade-off, you kind of repeating some codes that they will be like more robust with the noise. So like adding the noise level kind of increases your like decreases your like coding efficiency, but you're getting like more robust representation. So there is like simulation scenario where we don't have like noise, we'll have like perfect disentanglement, but we won't have like perfect disentanglement in the noise scenario. Like you probably have to like mix something like to be robust to the noise. So I'm just saying that like probably disentanglement is like more realistic, like more idealistic in the sense, but like we also have to consider like noise and how the like representation about anything have to be like robust to the noise. It's like noisy channel kind of idea from information theory. Like robust.
No,
code.
but yeah, but fundamentally, this is an information bottleneck, right?
You should say is or isn't.
Is like that's the whole point. Like it's a low dimensional representation of like it's a limited number of factors that represent the generative factors of the world. That's their point.
Yeah,
Yeah,
so.
I don't disagree with it. I'm just saying that we have to also assume kind of like dealing in the noise environment. But it's like another topic, I would say, yeah. So
No, but I agree with you. I agree with you that but I think it's like a difference between, so I agree with you. But the reason I think they didn't talk about it is that they just wanted to introduce the idea of like being disentangled to things.
yeah,
Because
I mean
it's
that's
been
fine.
like-
That's
it's
I
been
agree
like-
with that. I'm just saying that probably they need like in NeurIPS when you're writing paper, you have to consider what kind of cases or limitations. But
Oh, yeah.
And
No, I agree with that, sure.
maybe the idea of judging the model as a scientific tool based on some kind of task or discriminative score is erroneous. I think that's partly what Alex is getting at.
Is that it's wrong to use that?
Wrong, but if that is your limitation, then it's now less discriminative. What's the point in using it as a method?
But I don't know if it's less discriminative. You guys can change that. I don't know.
They can be though. No. What I just said was, if your limitation is that it is less discriminative,
Right.
why even bother with that as a metric?
Oh, a discriminative as a metric.
Yeah.
Yeah, I agree with that.
Because that is something that's common in the field.
No, I agree.
Especially in like all of the clips, everything. Some of them are really good at improving discriminative.
Yeah, so that's actually the funny thing is like, they don't at all, but so I think okay, let me rephrase the point. I think the point of this paper was just like, there's a lot of work on this in the VAE world, but it's not like commonly been like put back into the rest of the deep learning community, right? So that's what they're trying to do, and they're trying to relate it back to brains. And what they normally do as like a metric, nobody uses discriminative measures on VAE latent spaces. I've not seen that before. What people do is they have sources of information, and then they have a simulated data set. And then they correlate how well each dimension relates to that source of information to what the VAE finds after noise or nonlinear transformations. That's what they mostly compare it against, like mean total correlation, for example, is like a common way of looking at it. So I would actually say, and I think it's funny because I read this paper before it was reviewed by Carl Frost and among other people. And they've actually added a lot of references to nonlinear ICA and ICA by Equivariance into their paper now with the references, because it's essentially a similar kind of way of looking at it, right? Like they call it disentangling, which is like a new word they're using. But I mean, in a way, nonlinear ICA or ICA generally is also looking for these sources, right? Where in their case, they're saying that way of looking at sources, like attributes of objects, for example, is also what the brain is doing. And they're looking at it from a VAE standpoint and perspective, because that's what they've been working on. But it exists it has existed in the field before, generally. This idea of isolating the sources, which is ICA, right?
Yeah, ICA you can probably consider PCA,
Right.
because I don't think disentanglement is well defined.
No, yeah, I mean, they've tried to define it multiple times, actually, in multiple papers. So, but I think the point is like kind of to pull all together. But yeah, there's limitations, and I do agree, Alex, that there's a big chance that they are less distributed. Because that's also what I've been finding myself, with VAEs at least. Yeah. I think it's generally just a good idea though. My main takeaway was just more that we should be thinking about the data more to incorporate these types of things. That's why I also think the shortcut of just using VAEs is probably not the best argument to make. I think the best argument to make is what should your data be equivariant to, right? And that's important. Because even if you're doing classification, like a narrow AI task classification for in the clinic, let's say, then you still would prefer your model to be equivariant to certain things that you know are going to be occurring in the clinic and are not maybe in the training data.
The neuroimaging pipeline has for advantages. Like we're highly informed of like what types of transformations we do to already. So like if I were to approach this and like had a lot more time and resources, I would say that like replacing like each one of these transformations a piece at a time would be a manageable way to do it rather than sort of like try to solve general intelligence all at once. Like,
Yeah, I agree. Okay, I think that's it. Since everyone's left.